Okay, we're going to continue, and we're going to continue with we're learning how to write electronic configurations. Uh, this is what I gave you. I'm just going to do a few of them over here. Okay, lithium is 3 electrons. So if it's going to be 1s2, 2s1. Okay, you have to follow the off-pop principle. You can remember this: 1s, then 2s, then 2p, 3s, then 3p, 4s. And similarly, you can we can try and write the electronic configuration of bromine, which has a total of 35 electrons. So its electronic configuration is so its electronic configuration is going to be bromine is going to be 1s2. Okay, let's quickly do this. 1s2, 2s2. Then it's 2p6 following this table. Then 2p6, 3s, 3p, 4s. So it's going to be after 2p6, it's going to be 3s2. Then it's going to be 3p6. Then it's going to be 4s2. And after 4s, this is how many electrons? This is a total of 10, and another 10, that's 20 electrons. So we need 15 more electrons. So after 4s, you have 3d. So 3d is going to have 10 electrons. And then after 3d, you're going to have 4p and then 5s. So you're left with 5 electrons. So that's 4p5. So that's going to be your electronic configuration. So some of you sent me the work, and this is what you wrote for bromine. Remember to correct the order. To get this 3D and this 4s, the fourth shell should be on the outside, and the 3D should be on the inside. So that's how you write electronic configurations. But the next thing we're going to learn before moving on to the shortcut, the next thing is that there are two special cases whose electronic configuration. TK, I'm not sure if I've done this earlier, but there are two exceptions that you must remember, whose electronic configurations are kind of different compared to the others, just slightly. Basga, it's better that you correct the order. Okay, it's not required even if the order is not correct. Uh, why did this go missing? It's 1s2. Sorry, just 1 second. As I said, it's better that you correct the order. Uh, Otherwise, you would probably not lose marks for this. But it's better that the order of the subshells and the shells is corrected. Okay, when you're writing electronic configurations. Now remember there are two exceptions, and these are some two transition metal exceptions that the electronic configuration. For example, if you write for copper, it's going to be copper has 29 electrons, so that's going to be 1s2, 2s2, following the same pattern, 2p6. Then you have 3s2, 3p6, and then it's 4s2 and 3d9. I mean, according to the table, this, so according to the table, this is the electronic configuration that you're getting. But in reality, copper has this electronic configuration. Instead of 3d9, it actually has 10 electrons. And instead of 4s having 2 electrons, it actually has 1 electron in the 4s. So it's 3d10, 4s1. So you have to, so you have to remember this. And another exception that has to be remembered is chromium. It has a total of 24 electrons. So its electronic configuration is 1s2, 2s2, 2p6, so it's 2p6, then it's 3s2, 3p6, and The same thing, 4s2 and 3d5. Sorry, 3d4. But in reality, the electronic configuration is, instead of having two electrons over here, there's one, and over here it's five. So these are the two exceptions where you just, Usman, yes, the 1s means it's the first shell. What we talked about shells was, just going back, shells were energy levels. Okay, and 1 means that the energy level is low, 2 means the energy level is high, and 3 means the energy level is even higher. So the electron would be occupying a region that would be Busra. As I so what, coming back, 1 means low energy, 2 means higher energy, and 3 means even higher energy. That means the electron is occupying a much bigger orbital, and it would be occupying a region much bigger. TK, is this clear? Usman, is this clear? I said the next thing is, remember these two exceptions, that the electronic configuration is not going to be the one that you get from the off-war principle. TK, you have to alter it. Instead of 3d9, it's 3d10, and 4s is actually 1. And the reason for this is that, especially in these two cases, half-filled, and this only applies to these two elements, and there are more as well, but we're just going to stick with these two, half-filled and half-filled and completely filled configurations for these two elements are more stable. So especially these two. So remember these two exceptions, and you get tricky questions on this for copper and chromium. The next thing we're going to discuss is that how to write. I mean, what's the shortcut of writing electronic configurations? Okay, so we need to figure out a shorter way, uh, because it takes a lot of time to actually write all these electronic configurations. So what's the shortcut if you want to write an electronic configuration, if you want to know the electronic configuration of any element? The shortcut is that group 1, any element that's in group 1, its electronic configuration is going to end with an S with 1 electron. That's the valence shell for a group 1 element. So the outermost shell, that's going to be your valence shell. If group 2, then it's going to be S with 2 electrons in it. If there's an element in group 3, then the outermost shell is going to have S2 and P1 and so on. So we can write all of them. Group 4 would be S2, P2. Group 5 is going to be S2 and P3. 6 would be S2 and P4. 7 is S2 and P5. And 8 is S2P6. So these are the electronic configuration of all the elements of the valence shell, the outermost shell. Because we are interested in the valence shell because that's the shell that's involved in bonding, and we can discuss some examples. Like sodium has 11 electrons, so the electronic configuration is 1s2, 2s2, 2p6, and 3s1. So you can have a look, and the valence or the outermost shell is an S with one electron in it. Similarly, pick any other element, like if you pick sulfur, which we just did. So sulfur is going to be having 16 electrons. So that means it's going to have 1s2, 2s2, 2p6, 3s2, and 3p4. So sulfur's outermost shell is going to be this one. It's going to be 3s2 and 3p4. So there's going to be an S subshell and a P subshell. And one other thing is, how do you figure out whether it's going to be a 3s or a 2s, or I mean, without writing the electronic configuration? Because over here I've written only the subshell. I haven't told you how to figure out the shell. To figure out the outermost shell is easy. For any element, the period in which it is in the periodic table is the shell number. So for example, if we open the data booklet and have a look at the data booklet, and look at the periodic table, I said this is your periodic table. So if you want to know what the outermost shell is, like any element in the first row, that would be one. It would be shell number one. Any element that's in the second row, the shell would be number two. For example, sulfur is in the third row, so it's in the third period, so the shell number is three in that case. So it is three. It's coming out to be three. So hopefully, we're not interested in the initials. Uh, we're not interested because the initials are completely full. It's always the outermost shell that's involved in bonding. Those orbitals have electrons that are missing. They would be losing or gaining electrons. So you can always directly know the electronic configuration of elements by just looking at in which group they are and in which period they are. Okay, is this clear? Bazga, is this clear? Sanjita, Rida, is this clear?
Yes.
Acha, so let me find just one second. Let me find the worksheet. We're going to do atomic structure worksheet. This one, yes, about electronic configurations. Okay, some of it. Just one second. Let me. Acha, so we can start from this one. Okay, just to practice electronic configuration, which ion has the same electronic configuration as Cl minus one. This is same electronic configuration, so this is kind of easy. That Cl minus 1 has 18 electrons. So any element that has 18 electrons is going to have exactly the same electronic configuration. Scandium in the periodic table is 21. It's 3 plus, so it has 18 electrons. So scandium would be the answer. Uh, One thing that I've not discussed is, let me add that, what would happen if ions are formed? So remember, when ions are formed, especially when they lose or gain electrons, electrons are gained or lost from the outermost shell. I said they gained and lost from the outermost shell. And for example, if you have copper, copper's electronic configuration was, it was the N was 3d10 and 4s1. So if copper forms a plus one ion, then that means this electron, the outermost electron, is going to be lost. So remember that this is why the order, I was talking about the order in which you keep the outermost shell on the outside, because electrons are going to be lost from there. Because if you follow the offer principle, the order is very different, so you might miss that. Uh, so it's important that you keep the outermost shell right on the outside. Another very small thing about this is the electronic representation. There's another electronic representation. Okay, this is also something that I've missed. There's another electronic representation, and that is that instead, like if you write sodium, sodium has 11 electrons. So it's 1s2, 2s2, 2p6, and then 3s2, 3s1. Another way to write the electronic configuration is because you can directly figure out because you can directly figure out the outermost valence shell subshell, you can directly find that out. Okay, based on by looking at sodium, you can figure out that it's in the first group and it's in the third shell. So let me open the. So sodium, you can directly figure out what the outermost electronic configuration is going to be. It's in the third row, so that's third shell, and it's in group one, so that's S1, so 3s1. But before that, there's another way to write the electronic configuration that you use noble gases. So the 11th electron, you know the electronic configuration of the outermost shell. So before that, the electronic configuration of the rest of the element belongs to neon. For example, over here, this thing over here is neon with 10 electrons. So the other way to write the electronic configuration is that you write neon, put a square around it, that's 10 electrons, and the outermost is 3s1. And you can do this, you can use noble gases to represent electronic configuration of many different elements. So for example, let's talk about calcium. So calcium has a total of 20 electrons. First thing, I'm going to, instead of writing the electronic configuration of all the 20 electrons, what I'm going to do is I'm going to look at calcium. Calcium is in the fourth row. So that means it's in the fourth period. So that's 4. And it's in group 2. Group 2 would be S2. So calcium is going to be, the outermost shell is going to be 4s2. So the rest is 18 electrons. I mean, the 2 electrons are in the outermost shell. The rest is 18 electrons. So you go and have a look at calcium. What's the previous noble gas? That's with 18 electrons. That's argon. So you're going to use that. And you're going to put square brackets around it. And that argon represents the rest of the 18 electrons. Okay, is this idea clear? Rida, is this clear? Minail, is this clear?
Yes.
So let's. So we can think of any element, and you can pretty much follow the same pattern. Okay? For example, chlorine over here, the outermost, it's in the third shell, so that's it's in group 7, so it's S2P5, but that's the outermost shell. So chlorine with 17 electrons, the outermost shell is going to be S2, and it's going to be 3s2 and 3p5, right? Because it was in the third period. And before chlorine, the previous noble gas that comes is neon. So it's going to be neon. Followed by 3s2 and 3p5. This is a shortcut, okay? Without writing the entire complete electronic configuration, you can pretty much figure out what the electronic configuration of the element is. Then you have another thing, which is the other thing is that remember that group 1 and group 2 are going to be called your S block elements. And it's very obvious why you're going to call them the S block elements, because the last electron actually goes into an S block. So this is group 1 and group 2 would be referred to as S block. The rest are going to be referred to as your P block, because the last electron is actually going into your P orbital. So they're referred to as P block elements. So if you have a look at the periodic table, this is your P block. I mean, this entire thing. This is your P block, and the group 1 and 2 are your S block. As I remember, in the newer periodic table, group 3 is 13 and 4 is 14. So just make sure you remember this. And then you have your transition metals. The transition metals are in the middle. And transition metals, and the first thing is this block over here is not actually, technically, it's not transition metals. Most of them are transition metals, but not all of them. The correct term used for this middle block is, they're called D block elements. So the D block elements are your elements that are between group 2 and group 3, or group 2 and group 13. Incorrectly referred to as transition metals. Although most of the times they are referred to as transition metals. So we can say, I mean, the only reason we're not going to refer to them as transition metals is because not all of them, 90% are transition metals, not all of them. So incorrectly referred to as transition metals. It's a chapter in A2. You're going to study this chapter in A2 for transition metals, and you'll figure out why they're not transition metals. Some of them are not transition metals. Now, why do you call them D block elements? Because the last electron, according to the Off-Bohr principle, goes into a D subshell. According to the Off-Bohr principle. For example, iron over here has a total of 26 electrons, so that's 1s2. If you write the electron in 1s2, 2s2, 2p6, then you have 3s2, 3p6, and then you have 4s2, and then 3d would have 6 electrons. So the last electron, according to the Off-Bohr principle, goes into the D subshell. But remember, no one is actually filling electrons. The electrons are always filled in an atom. Since the universe has been made, the electrons are always there. So but according to the Off-Bohr principle, the last electron actually goes into a D subshell, which is why they're called D block elements. And the D, in most cases, would usually be empty, not completely full. In some cases, it will be like zinc, it will be full, but in most cases, it will not be completely full. So these are D block elements. Now, is this clear to everyone? Bazaka, is this clear? Rida, is this clear?
Yes, sir.
Achha, now coming. Now, coming back to the worksheet that we were doing. Where did it go? 1 second. Achha, this one. Which of the part? Now, this is a tricky question. Which of the particles would, on losing an electron, have a half-filled set of p orbitals? Half-filled set of p orbitals. Now, I mean, there's a lengthier way of doing this question, which is that you write the electronic configuration of all the elements. But I mean, that's the whole point. You don't have a lot of time in your AS MCQ paper. So what you're going to do is half-filled set of p orbitals. I'm going to look at the table that I drew over here. Half-filled p orbitals. Which group has half-filled p orbitals? It's group 5, right? Group 5, the electronic configuration, the p is going to be half-filled. P usually has 6 electrons, but now over here it has 3 electrons. So we're looking for an element that's in group 5. So we're looking for an element that's in group 5. Now, if you look at the periodic table, group 5 either has nitrogen, which has 7 electrons, or phosphorus, which has, I think, 15 electrons. You write the electronic configuration of any one of them, it's going to give you a half-filled set of p orbitals. Okay, so it's either nitrogen or phosphorus. But the question states that the element must get that electronic configuration on losing an electron. For example, over here, nitrogen -1. -1 means that instead of 7 electrons, it has 1 extra electron. So if it loses an electron, it's going to have how many electrons? It's going to have 7 electrons. So it's going to have exactly the electronic configuration of a group 5 element. Hence, this is going to be your answer n-1, because he had explicitly stated that the element must lose an electron to and then get the electronic configuration where it has a half-filled set of p orbitals. So it can't be nitrogen, because if you take nitrogen, nitrogen has 7 electrons. So if it loses electrons, it now has 6 electrons. Now 6 electrons is not going to be the group 5 electronic configuration. TK, is this clear? Minahil, is this clear? Usman, is this clear?
Yes.
So the next one is, what is the order of increasing energy of the listed orbitals in the atom of titanium? TK, for this, I said this, remember, is a very old question. But the new and examiner report also pretty much states the same thing. The new, I've already told you that the 4s must be kept on the outside. Okay, the 4 shell is the higher energy shell. So the electronic configuration of and the answer to this order of increasing energy level is going to be this one. ठीक है बाज़ I'm going to explain 5 again. बाज़ ये क्लियर था कि half filled set of p orbitals किसके होते हैं? ये I told you कि group 5 के होते हैं. Group 5
ये क्लियर है, ये
ठीक है.
क्लियर है.
अच्छा, so half filled set of p orbitals. लेकिन उस he had explicitly stated that on losing an electron, मतलब after losing an electron. अब group 5 has 2 atoms, nitrogen and phosphorus, right? Nitrogen has 7 electrons, phosphorus has 15 electrons. So both of these electronic configurations are going to have a half-filled set of p orbitals, ठीक है? मतलब इसका करोगे तो it's 1s2, 2s2, 2p3. This one would be 1s2, 2s2, 2p6, and then 3s2, 3p3. So we're looking for an element that either has 7 electrons after losing an electron or 15 electrons after losing electrons. So nitrogen -1 के पास कितने electrons होंगे? It's going to have 8 electrons क्योंकि it's -1. So if it loses electrons, तो कितने electrons हो जाएंगे? 7 electrons.
Okay, ठीक है, I understood. सही है, exactly.
अच्छा, next one is gallium nitride is an ionic compound, और उसने कहा कि what's the electronic configuration of the nitrogen ion? That's easy. N-3. So that means it's going to have 7 electrons वैसे. So now it's going to have 10 electrons. So 10 electrons is going to be 1s2, 2s2, 2p6. This one, in which pair is the radius of the second atom greater than that of the, as a radius? In which pair is the radius? Maybe I haven't talked about the sizes of atoms yet. I said this one. The question states, I'll just explain the question. The question states that which graph represents the number of unpaired p orbital electrons for atoms from proton number 13 to 18. So he's asking ke unpaired p orbitals. So he's asking if an element has 13 electrons, okay, this first one, I've written down the electronic configuration. 13 electrons is going to be, you can either write the whole electronic configuration, or 13 is group 3. Group 3 is going to be 3s2, 3p1, or simply s2 and p1. 14 is going to have exactly the same electronic configuration, except it's going to have s2 and p2, and so on. Then you're going to have s2 and p3, then s2 and p4, s2 and p5, s2 and p6. So that's 18 electrons. Okay, so no need to write the whole electronic configuration. Now he's asking to plot a diagram or a graph where 13, 14, 15, 16, 17, 18, that's the proton number, and you list the number of unpaired electrons. So unpaired electrons, how do you figure out unpaired electrons? If you have 3p1, what does that mean? The 3p subshell actually has three orbitals, 3px, 3py, and 3pz. Now, if it has one electron, that means there's one electron over here, but the rest of the orbitals are completely empty. So how many unpaired or half-filled orbitals does it have? It has one. Okay, so the first one is going to have one. The second one, if you have 3p2, so that means there's going to be one more electron in the 3py. So if it's 3p2, the number of unpaired orbitals would be 2. Then if you have 3p3, that means the third orbital would have one electron. Always remember, orbitals are filled in a single manner first in a subshell. So now the total number of unpaired orbitals would be 3. I'm going to write that over here. Now, if you have 4 electrons in the p, so that means the first one would have 2 electrons. So now the total number of unpaired orbitals, the first one is paired now. It has 2 electrons. So the other 2 orbitals would be unpaired. So you're going to be back to 2. Then proton number 17 would be 3p5. 3p5 would be this one. The 3p orbitals would be 2, 2, and 1. So the number of unpaired orbitals would be 1. And if it's 3p6, then all of them would be paired. So it's going to be 0. So the number of unpaired orbitals, it goes from 1, 2, then 3, then it starts decreasing 2, 1, 2, 0. So the graph is going to look like this. Okay, it's going to be D. Is this clear? Sajida, is this clear? Rida, is this clear? Minahil? Bhaskar?
Yes.
Yes.
Achha, so next question. What could be the proton number of an element that has 3 unpaired electrons in each of its orbitals? In each of its orbitals, 3 unpaired electrons. That is definitely going to be this one. P3. P3 is going to have 3 unpaired. So you're basically looking for an element in group 5. So group 5 is this one. Okay, you're going to have a look at the periodic table. Where's the periodic table? So group 5, if you look at group 15 over here, it's either 7 or 15 or 33. They're all going to have the same outer electronic configuration. So remember, the number one mistake most people do is that they actually waste a lot of time. They start writing these electronic configurations. You don't have to do that. Okay, remember, there are shortcuts to figure out what the electronic configuration is going to be. As the next one, this one as well, in which group it is. So the outermost shell, if you look at the outermost shell, it's S2 and P6. Go and have a look. S2 and P6 is this one over here. It's a noble gas. So it's going to be group 0. In the newer periodic table, it's not group 0. It's now referred to as group 18. So remember this change. These things in the older past papers, things were different. The periodic table was different, but now these are labeled differently. As the next one, in which species do both species have the same number of unpaired p electrons? Again, you have to count the number of unpaired electrons. You don't have a lot of time. You just have 1 minute to solve this question. So oxen is in group 6. So what's the electronic configuration of oxen in group 6? It's going to be S2 and P4, I think. Group 6 is S2 and P4. So this is S2 and P4. What about chlorine? Now remember, this is not actually chlorine. Chlorine has 17 electrons. It's chlorine plus 1. That means it has lost an electron. It's 16 electrons. So where do you have 16 electrons? 16 electrons is this one. So it's again group 6. So the electronic configuration would be of that of sulfur. Like chlorine has 17 electrons, but it was chlorine plus 1, so that means it has lost an electron. So the electronic configuration would be of sulfur. So it's going to be S2 and P4 as well. So they're both going to have exactly the same electronic configuration. If they have the same electronic configuration, they're going to have the same number of unpaired p orbitals as well. So one is definitely going to be, it's definitely going to be correct in this case. Is this clear? Bhasgar, is this clear? Just similarly, the next one, you have fluorine plus 1. Again, fluorine plus 1. Fluorine plus 1 would be fluorine losing an electron. So fluorine is 9 electrons. Plus 1 means that you have the electronic configuration of oxygen. You have 1 electron less. 9 electrons, instead you're looking for electronic configuration with 8 electrons. So it's group 6. What's the electronic configuration of group 6? It is S2P4. What about gallium minus 1? Now minus 1 means 1 extra electron. So you have, look at the periodic table, find gallium first. This is gallium. Now gallium is minus 1, which means move 1 forward. So you're looking for this electronic configuration. This is in group 4. What's the electronic configuration of group 4? Group 4 is S2 and P2. Now the thing is, these two have different electronic configurations, but you have to be careful. Do they have the same number of unpaired p electrons or not? This is P4. So I'm going to write the electronic configuration of P4. What would P4 look like? P4 would be, the p subshell would have px, py, pz, 4 electrons. How would you fill 4 electrons? First, 1 electron in each of them, and then one of them would be having 2 electrons. So this is the electronic configuration of P4. What's the electronic configuration of P2? It's going to be px, py, pz, 1, 1, and 0. Now, if you count the number of unpaired orbitals, that's 2 over here. And over here, the unpaired orbitals are also 2. One of them is full, the other 2 are unpaired. So the number of unpaired orbitals is still the same. So 2 is also it's definitely correct. The last one, number 3. Phosphorus is in group 5. Group 5 is S2, P3. So P3 means 3 unpaired orbitals. Like P3 means 1 electron in each of them, 3 of them unpaired. And then you have neon plus 1, which means neon lost an electron. So neon had a perfect electronic configuration of P6, S2P6. But now it has lost an electron, so it's going to be the electronic configuration of fluorine. So that would be S2P5. Now these two clearly have different number of unpaired orbitals. Over here, there are 3 unpaired orbitals. Over here, most of them are full except for 1. So 1 unpaired orbital. So third one would be incorrect. Okay? Is this clear to everyone?
Yes.
So let's do the last one, which is an atom has 8 electrons. TK, we talked about this box representation. This is 1s. I mean, it's the same thing. It's 1s, 2s, 2p subshell, then 3s, and so on. So the orbitals would be represented by boxes where I told you about the opposite spins. Now the electronic configuration of 8 electrons. 8 electrons would be 1s2. So it's probably going to be this one, 1s2, 2s2, and 2p4. 4 electrons in the 2p would be first, they get half filled, and then one of them would be paired with the opposite spins. So B is going to be your answer to this question. Okay? So any questions about this? Is this clear? Okay, I'm going to send this on the group as well this worksheet. ठीक है? So we're going to continue with this, probably move towards chemical bonding tomorrow then. So, okay. Take care, Allah Hafiz.